The name of this video is Line Toroidal Solenoid M. In fact, we are going to compute the mutual inductance M between an infinite straight line that carries a current I in this direction and a toroidal solenoid which has this line of current as the rotational axis or evolution axis, gamma z. So let's sketch this problem. And again, I will only sketch half of the problem because it's symmetric. And so in this case, we have this is our gamma z-axis, or also the z-axis of a cylindrical coordinate system, which carries a current, a DC current I on it, upward in this direction, same direction as gamma z. Then here we have our r-axis. This is origin. This one is var phi, which goes inside the board, if you want. So this is u var phi inside the board, okay, here. And let us sketch finally the structure itself, which looks like this. A rectangular is always, for simplicity, core for the toroidal solenoid. This point here is capital R1, smaller than capital R2 as before. This point here is point Z0 as before, and this point here is point Z0 plus H, right there. So H is the height of this rectangle, which carries no current, because in fact in this case we could either calculate the mutual inductance M between 2 and 1, so due on 1 due to 2, or equivalently we can compute M1, 2 on 2 due to 1, which is in fact what we're about to do. So we want to compute the mutual inductance, which are the same as we will prove in Phys 342. So here we have a current I, and let's call it in fact I1. So we set the current I2 equal to 0 here. And typically, remember that the orientation of this loop in the toroidal solenoid was like this, so same as U var phi if you want, but I will choose this time for pedagogical reasons exactly the opposite. So something which goes this way. So this is gamma of one loop at 2, okay? So that the unit vector n L2 associated with this loop is actually the opposite of U var phi, is minus U var phi. Okay, let's keep that in mind for a reason which will become apparent in a few minutes. Again, I could compute the magnetic field due to the toroid and see the effect on the line, or vice versa. It's simpler to do the line on the toroid. Okay, and the procedure is that first we calculate the flux of the line magnetic field on one loop of the toroid, and then we multiply times n as always. So one loop means over this area here, which we call capital sigma L for one loop 2, because it's the second structure. But again, we set I2 equal to 0. We switch it off if there was anything, otherwise we keep it 0. So it's just a conductor, which can carry, of course, a current. Okay? All right. So now that we have all this information here at hand, and of course it's symmetric on the other side, so basically again, it's a line with the torus around it, and this is the rotational axis of the torus, as well as the line of current itself. So we already know that the magnetostatic field B, D1, due to the current I1, is equal to mu naught times I1 divided by 2 pi r u phi, u r phi. Okay, so we know that. Now, we want to compute the flux through one loop on 2 due to 1. So this is the surface integral on sigma L2 of B1 is the flux due to 1 on 2 n L2 dA, where dA is an infinitesimal area element over here. Okay, so this one we can rewrite it with respect to this coordinate system. All constants go out the sign of integral. So it's mu naught, which is a constant, I1 divided by 2 pi. Then we have u bar phi. This, let's do it. So here we have the integral between z naught and z naught plus h in dz. And the other part, let's do it properly down here, is between capital R1 and capital R2 in dr of u bar phi from here, dotted with NL2, which is minus u bar phi, and this one times 1 over r, which is the integrand here. And so the final result is mu naught I1 h divided by 2 pi. This one gives us a minus sign from this dot product, natural logarithm of R2 divided by R1. So it's similar to what we found before with the negative sign and without capital N. There is no N here. It's just the field of an infinite line. Now that we have that, we can easily compute the overall flux associated to 1 with all loops, which is going to be n times f phi L to 1. And so this is going to be minus mu naught n I1 h divided by 2 pi natural logarithm of capital R2 over capital R1. And finally, from the definition of mutual inductance, m to 1 is nothing but phi to 1 divided by I1. So we get rid of this I1 here, and we obtain nothing but minus mu naught n h divided by 2 pi natural logarithm of R2 divided by R1, where in this case, let's discuss about a few features of this in a second. So this is our final result for the mutual inductance here. Very important result. M12 would be exactly the same if you want to compute that. In fact, we were computing this one. Not this, but this, M21, obviously, as we've done here. And so, again, they are the same. So what is interesting is that this quantity, it's clearly negative. And I've chosen on purpose this orientation here on this line instead of the usual one to show that I can get a negative mutual inductance if I choose some strange orientations. So check on that, negative sign, that's fine. Also, it depends on n instead of n squared, because we have a weaker field due to the infinite line compared to that of n loops in a toroid. So compared to the self-inductance of a toroid, it scales with n instead of n squared in this case, so it's weaker, okay? So that's an important property. It's negative and it's weaker compared to the one we calculated before. And so to summarize this video here, we wanted to compute the mutual inductance between an infinite straight line and a toroid which has the line as central axis, as rotational axis, but choosing an interesting convention so that the mutual inductance ends up being negative. We do all the fluxes, we multiply times n fluxes, of course, in this case here, and we get the usual natural logarithm dependence, which is positive, but then with this negative sign, the whole thing is negative. And obviously, we get only n instead of n squared as a final result here. That's it.